And like, or what is the current plan for like virtual kids taking exams?
I don't have a great answer for that, except that all my virtual kids have agreed to come in and take their exams here after school. I mean, every test they take after school, which is huge for me. They've helped me survive. I think I'd be gone by now. I was drowning at the beginning of the year. I was just here from 6:30 to 7:30 every day. I was like, this is not a good way to live. But they all agreed to come in after school, so I don't have to make out those tests anymore. I can just give them the same tests or some common version. So that's been huge for me. They really just saved me. So I would assume they would just continue to come in. They'd probably come in someday at like 1. And I think all those guys have said they're coming back. Is that right? Thinking all of them. So everyone that I know of, right? You're all coming back? But I think they said they're all coming back this semester, next semester. So you'll get in this class, although you never know, sometimes the schedules get shuffled around, but Yvonne, Fallon, and, I take that back, I think Sid's not, but Yvonne and Fallon should be coming back, and Haddam is coming back, but I don't know if they'll end up being in this class, because sometimes their schedules don't balance. So like I know Anderson was in my 7th period, but when they brought him back, they shuffled the schedule and ended up in the 1st period. So who knows where they'll end up. But anyway, so let's take a look at these. Now, this particular kind, I call them strange sums, because I actually remember, it's probably 20-something years ago, and I was trying to figure these out, and I actually figured them out on my own. I was so proud of myself. And then I bought this book called The Art of Problem Solving. And it was written 20 years prior. And of course it had a detailed explanation of everything I spent like 20 hours trying to figure out. And I was like, great. But before I read that, and I call them strange sums because that's what that guy called them in his book. And a lot of what I know I've learned from this book, it's actually written by a guy from Austin, Alabama, this genius kid who just showed up out of nowhere. And he actually was so smart, he tested through all these protocols and ended up in the International Mathematics Olympiad, representing the country of the United States with college kids, and made a perfect score on it. And he was from Austin, Alabama. And y'all are like, where the heck is Austin? Some of you might have played Austin in a sport or something, but I think they're like an hour north of here. But yeah, this brilliant guy wrote this book. It was basically how to be really good at math tournaments. And I bought both volumes and learned a bunch. But anyway, this was something I actually noticed about a pattern of this. And when you're looking at these, here's the key to this first kind of strange sum. You look in here, and the numerators all end up being the same number. Now, I wrote them all as 1s, because even if they were 2s, you could factor the 2 out. If there were 7s, you could factor the 7 out, and then it would look like this, and you could solve it, and then go back and multiply by 7 or multiply by 2. So I've treated them all like they're 1s. But remember, you could still do these if it was 5, 5, 5, or 10, 10, 10, or whatever. All right? So the pattern is, you see the initial number and the number that it's with are separated by the same amount. So it might be like 3, 6, 4, 7, 5, 8. They all have a difference of 3. Now they actually don't have to go 3 here, 4 here, 5 there. That's not the key. The key is that they're separated by the same value. Okay, and sometimes it's multiplied together. Sometimes it would be 1 over 18, 1 over 28, 1 over 40. So it might look like it's geometric, or it might look like something else. And it's one of those things, and by the time we get finished with this unit, your goal will be to go, you look at a problem and you go, crud, I don't know what it is. So you just start checking. Is it arithmetic? And if you remember arithmetics had the same thing added each time. And you would go, well, no, it's not arithmetic. And then you go, well, is it geometric? Geometrics, you're multiplying by the same thing every time. And there's ways to check this that we'll talk about as we go through. And as you'll go down your list, at some point you'll go, is it a strange sum? Strange sums have, when the number on the bottom is factored like this, you see that pattern where they all have that difference of 3. And also, they do usually have a pattern with the lead numbers. It doesn't have to be 3, 4, 5. Like sometimes you'll look at these numbers and it'll go 3, 6, 6, 9, 9, 12. But you'll see a pattern on the lead numbers. And the lead numbers pattern would be arithmetic. 3, 6, 9, 3, 4, 5. And then the difference between them will always be the same. So you'll notice these after a while, but these, this is the first kind of strange sum we're going to talk about today. We're going to talk about two different kinds. So, all of what I'm showing you here is what I discovered in the process when I was learning to figure these out. You don't have to do all of this when you're doing it. I just want to show you the why, and then when I show you the why, you should be okay in actually doing it yourself. So here's what I discovered. I discovered anytime you have a fraction with two numbers on the bottom, that you can rewrite this as a product of two things. And the product is 1 over the difference in these two numbers. Okay, so like if my number was 1 over 3 times 5, I can rewrite it as a product of 1/2. 1 over the difference in these two numbers. Are you following me on that part? And then the other thing you multiply by is basically 1 over this minus 1 over this. 1 over this minus that. So on a 1 over 3/5, I could rewrite that as 1/2, because 5 minus 3 is 1/2, and then 1/3 minus 1/5. Now you might go, why would you ever want to do that? Well, take a look and make sure you understand that this is true. Just to double check this, if I wanted to subtract those, I would need a what? Common denominator. And I would get 5/15 minus 3/15 is 2/15. And 2/15 times 1/2 is 1/15. And this is 1/15, right? So it does actually work. Now, if I rewrote every fraction like this, this is what I would, and rewriting it in this weird form, each one of these right here becomes this, etc., etc. And I'm even going to simplify it a little bit more. Instead of writing it as like 6 minus 3 right here, or 7 minus 4 right here, I'm just going to go 1 over the difference, 1 over 1/3, 1/3 minus the 6th. 1 over the difference, 1/3, 1/4 minus the 7th. 1 over the difference, 1/3, 1/5 minus an 8. And then hopefully you can tell, if it's going 3, 6, 4, 7, 5, 8, what's the next one? 6, 9. Then 7, 10, 8, 11. Are you with me? And it's going to go that way forever, because it said ... Well, now what can you do? If every one of these has the same difference, and again, that was one of the keys to these problems, you could factor out a 1/3 out of everything. So if I factor a 1/3 out of every one of these, now I'm left with this. And this, are the parentheses doing anything anymore? They're not doing anything anymore. Now I left them there to help you see the grouping, but here they were separating it from the 1/3. But now they're doing nothing since the 1/3's out. Well, at this point you can go, oh, well then what cancels? And as you look through here, you'll start seeing, well, that negative 1/6 and that positive 1/6, and that negative 1/7 and that positive 1/7. And then here's the key. The second you cancel something, and back-to-back terms are canceled. See, before this, I didn't have back-to-back terms, right? I canceled these two, but there was something in the middle. I canceled these two, but there was something in the middle. But the second I cancel something, right here, and it's back-to-back terms, then that's going to let you know that everything else is going to cancel. Not this one, and not this one, and not this one. But at this point, look, that next term would have been 1/9 minus 1/12. 1/9 is going to go. The next term would have been 1/10 minus 1/13. 1/10 is going to go. Next one would have been 1/11 minus 1/14. 1/11 is going to go. The second I see back-to-back, that means everything cancels if it's infinite forever and ever. Because it's infinite. And what do you have left? 1/3. And you can see all these cancels right here. 1/3, and all that's left is the 1/3 there, the 1/4 there, and the 1/5 there. Everything else is gone, so you bring down those three things, you find a common denominator and add them, which is a little annoying, I hear you, and then you just multiply by 1/3 again. Are you seeing that? And the only difference here is, what if it's not finite? Well, if it's not finite, check this out. What if it went plus ... plus, and then instead of ending it, instead of going forever, let's just say it went to 20.23. Well, if that happens, here's a nice little trick for you. If you have 3 terms in the front, like 1/3, 1/4, 1/5, do you remember this part? If I rewrite this all the way out, this thing, I'm gonna get rid of this, but this thing would have looked something like this at the end. It would have been like 118 minus 121, 119 minus 122, 120 minus 1 over 23. And it would have ended right there, that last term. But as you cancel, guess what would have happened? As you cancel, everything's canceling, right? Back the 7 and the 10, the 8 and the whatever, the 1/7 and the negative 1/7, the 1/8 and the negative 1/8. This is what would have happened. All of these terms would have canceled all the way through here, except the last 3 negative terms. So if you end up with 3 positive terms up here that started with 1/3 and went 1/3, 1/4, 1/5, then you're going to end up with 1/23 in the back, 1/22, 1/21. But the front ones are the positives, and the ones at the back are the negatives. And if you can remember that, that's a great way to not have to waste so much time. Now, sometimes you don't have 3 terms in the front, you have 2. If you have 2 positives in the front, then you have the last 2 negatives. Sometimes they aren't consecutive. They don't go 1/3, 1/4, 1/5. Sometimes they go 1/3, 1/5, 1/7, and they skip every 2. If that's the case, skip every 2 here. Write negative 1 over 23, negative 1 over 21, negative 1 over 19. And I'll do a few of these and you'll see it. But that keeps you from having to write out every one, because who wants to do that if the number is like 1 over 120 and 123? Do you really want to write out all those terms and see the canceling? I certainly don't. But this is a way you can go about doing these, and you'll see once you get the pattern down, it's not as much effort as you might think. You really can get a groove for these, but don't just purely memorize your way through it. Have a general understanding of what's happening, and then create your own shortcut or whatever that helps you. But let's do a couple of these before we look at that next kind. So like this one is a little bit different. So let's take a look at it. So right here, if you were writing these out, and I'm going to write it out one time like this, and then I'm not again. If I was writing each one of these terms out, it would be, the difference is what? 2. So it would be 1/2, and then you'd go 1/3 minus 1/5. And then, right here, 1/2, and you'd go 1/5 minus 1/7. And then you go 1/2, 1/7 minus 1/9. Now, I will never do that again. Here's what I'm going to do. If they're all going to end up having a 1/2, this is what I would do if I were you. 1/2, and then go 1/3 minus 1/5, positive 1/5 minus 1/7, positive 1/7 minus 1/9. And if you need to write a couple extra ones, positive 1/9 minus 1/11, positive 1/11 minus 1/13, ... Are you seeing this? And then, so you don't have to do that again, although it's helpful to understand the why, I guess. At this point, what starts canceling? Now, the great part about that right there, you just cancel back-to-back terms. That's the flag that goes up and says, the second you do that, everything else you know is going to cancel. Now, that was really nice on this one. On the other one, you canceled 2 terms and you didn't have back-to-back. Canceled 2 more, you still didn't have back-to-back. Took to the 3rd one before you saw back-to-back canceled terms. Then you go, okay, everything else from that point on. But at this point, it's pretty obvious everything else is canceling, right? Forever and ever. So how many terms do you have at the front? Since it was infinite, you don't even have to worry about the back. But what if this thing was like, what if it was that? Well, if you have 1 positive term right there, then you're going to have 1 negative term right there. So if it did end like that, you would go, oh, everything cancels until the negative 1 over 33, and you would take that term and this term, you'd add them together and multiply by 1/2. But in this case, we don't even have that. It goes forever, so we don't have to worry about anything other than 1/2 times 1/3. We're done. Now, this one is just math tournaments trying to get you to curl into the fetal position or assume the position or have great fear and trepidation. But we don't do that. What do? We do not assume the position. And we look at these and we go, you know what? There is one thing I can do. It's a sigma notation problem, right? What can I do? Come on. Yeah, even before that. I mean, he's right. Write all of the terms out. But even if this number was really big, I can at least write one term, right? So start with something you can do, and that would be plugging the 1 in, or whatever that number is right there on the bottom. So if I plug the 1 in, don't even clean it up. What do you get? You get 1 over 2 times 1 plus 1 is 3. Plug a 1 in there. 2 times 1 plus 3 is 5. Okay, I'm not even going to write 15. I really want to see what's happening. And then sigma means the sum of. So then I plug a 2 in. 4 plus 1 is 5. Times 4 plus 3 is 7. And then I plug a 3 in. And then a 4 in. And I keep on going until the very end. Now this one had a 5, right? So we're going to keep on going all the way through the very last one. And the very last one would be 11 times 13. And you look at this and you go, well, that's one of these problems. Common difference between the denominators is 2, right? If I subtract them, technically it's negative 2, but you get the idea. We're doing that minus that. 5 minus 3 is 2. You just look at them, it looks like it's a negative 2. But anyway, so I'm going to pull out a 1/2, and I'm going to write a 1/3 minus a 5th. A 5th minus a 7th. And I'm going to keep doing that all the way through a 1/11th minus a 13th. And I tell you what, I'm going to write all these out just so you really see it at least once. A 7th minus a 9th, a 9th minus an 11th, and an 11th minus a 13th. And this is what happens even when the powers are really high. Cancels. Oh look, I cancel back-to-back terms. If it was infinity right there, what would that mean? Everything else cancels. Because it's not infinity, that means you have one term remaining on the front that's positive. You're going to have the very last term remaining that's negative. Look, everything else cancels. So you take those two terms, the 1/3 minus the 1/13, you add them, or subtract them in this case, and that gives you 10 over 39 when you find a common denominator. And you multiply it by half, and I believe you get 5 over 39. Not too bad? And you can also sometimes guess, sometimes they're not going to have it factored. That was a big hint for you. Sometimes it won't be factored. Sometimes you'll see 4x squared plus 8x plus 3 down there instead. In that case, when you're doing the sigma, you're probably going to get 1 over 15 plus 1 over 35 plus 1 over 63. And it's not going to look that pretty. And those are the kind of problems where you go through there, and I would probably think it's arithmetic or geometric at first. And I would check the common ratio, which we'll talk about tomorrow, and you'd go, oh, it's not geometric. Now what? And then you start going, and at some point I go, wait, 3 times 5, 5 times 7, 7 times 9. Oh, it fits one of these patterns. So this is just going to be one on a long series of checklists you go through on your test when it comes to sequences and series. And if you have that checklist down, it's not that big of a deal. But it is going to be a little bit more than you learned last year, because we're going to throw in quadratics and a couple others. But hopefully you remember some of this, so this part won't be as bad. So let me show you a couple more of these, and then we'll get to the second kind that we have. How about, all right, look at 2b. So I look at this, whether I say simplify or find the sum or whatever, I'm looking at it and going, oh, they want me to add these fractions together. The numerator is the same all the way through. The denominator has that pattern where the difference is 3, right? So that tells me that I bet it's going to fit this form I have. Now the 2 I'm not comfortable with, or super comfortable, because I'm used to seeing a 1 up there. So I'm going to go ahead and factor that 2 out. So that, when I factor it out, that basically leaves a 1 on the top. And then at this point, how would you have done this problem? What goes out front? So the difference is 3. So out front, I do a 1/3. But this time, since there's already a 2, it's a 2/3. And then what goes on the inside? 1/4 minus 1/7. 1/7 minus 1/10. 1/10 minus 1/13. Plus dot, dot, dot. 1/22 minus 1/25. And on this one again, and then we're going to get to some of the uglier ones, as soon as you start canceling, you get back-to-back cancels. And you see, oh, if that happens, they don't cancel forever this time because it's not infinite. But I do have one term left in the front that's positive. Go take the very last term that's negative. Subtract those. And in this case, multiply by 2/3. So this time I get 21 over 100 times 2/3, which gives me 7/50. And by the way, I know it's been a long time since you just added fractions, but since you're going to be doing that a lot, do you know how to add fractions real quickly? Just go 25 times 1 minus 4 times 1 over 100. 25 minus 4 over 100. It's just a real quick way of finding a common. It may not be your smallest. It may not be your least common denominator, but it will be a common denominator. It's just a quick, easy way of doing it without going, okay, let's find the common denominator. And if you really think about it, look, common denominator, isn't that really what I'm doing? 4 times 1, 25 times 1 over 100, and then you subtract. So it just saves yourself the trouble. 25 minus 4 over 100, done. Cancel 2's, cancel 3's. Just makes it a little easier. You don't have to think so much about the process. And you're going to be doing this a decent amount on these problems. All right, let's try something a little bit different, but still the same model. All right, look at number 4. Number 4, again, I look at this. The numerators are the same. The denominators are all separated by the same number. I've checked those boxes. It doesn't go forever. There is an ending term, but I can get started. So what comes out front? 1/2. What do I write in the parentheses? 1 over 1 minus 1 over 3. Plus 1 over 2 minus 1 over 4. And nothing's canceled yet. Plus 1 over 3 minus 1 over 5. Now something is canceled at this point, but I'm going to keep writing. What would the next term be? Good, and then 1 over 5 minus 1 over 7, dot, 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 all the way through 1 over 9 minus 1 over 11. Now, as I start canceling, negative 1/3, positive 1/3. Nothing back to back yet. Negative 1/4, okay, right there. The second I hit negative 1/4, I got back-to-back terms. That tells me that there's going to be a run of consecutively canceled terms. So how many terms were left in the front? 2. So if I have 1 over 1 and 1 over 2 in the front, which are like these, then what am I going to have in the back? Negative 1 over 11th and what? Negative 1 over 10. Because this right here increased by 1, this will decrease by 1. So you could write those out if you want. There was actually a positive 1/8 minus a 1/10 there. But you don't have to. I just say, okay, if 1 over 1 plus 1 over 2 is there, then negative 1 over 11, and if this is increasing by 1, this would have been also patterned in the same way. But again, the ending ones are negative, beginning ones are positive. Well, that's going to be a little bit annoying to add these together. But you could do the same thing I just did. And by the way, those were to subtract fractions. On these, I would probably just find a common denominator. So what would your common denominator be here? 110. So I'm going to multiply the top and the bottom by a 110 here. Here, the top and the bottom by a 55. Here, the top and the bottom by an 11. And here, the top and the bottom by a 10. And then I would add this up. So 165, 155, 144 maybe. So 1/2 I think that's right. 165, 155, 144. So I end up with 144 over 110. And that cancels and leaves me a 72 over 110, which is a 36 over 55. I think. Hopefully I did the math right. Y'all with me? So that's it for these. I mean, I can find a way to make them look ugly with sigma notation. You can see on number 5. Listen, I know what this is in a way because I made the problem and I shoved it in this section, but if I saw this on your test, my first inclination would be, oh yeah, it's geometric and I'm multiplying by 1/7. See that? But when I multiply by 1/7 again, I don't get this, do I? So that makes me go, oh, great, it's not geometric. What else could it be? So I think, well, and I go down my checklist, which you will have by the end. Is it arithmetic? No. Is it geometric? No. And you'll have ways to check those. At some point I go, oh wait, if I refactored that, 1 times 4, 4 times 7, 7 times 10, and if you're looking at it and go, well, how did you know to factor it that way? Why didn't it 2 times 2, and 2 times 14, and 14 times 5? Well, it does factor that way, but I don't see a pattern. So again, there's some guessing and checking and revising along the way. It's not like completely going to be spoon-fed to you. Sometimes you got to think a little outside the box, but the second I see the pattern, I go, oh, there you go. How would I set this up? 1/3 on the outside, 1 over 1 minus 1 over 4, 1 over 4 minus 1 over 7, 1 over 7 minus 1 over 10. This is infinite. Second I see back to back, that tells me everything else cancels. It goes on forever. 1/3 times a 1 over 1. And this is the kind of thing you see as a ciphering question. Yeah?
Can you not see that, like, when it's going to cancel, like, before you even write out all the fractions?
Sure, on this one. Yeah, and there's some shortcuts you can take, but again, if you memorize shortcuts for these and you really don't understand the process, then when it doesn't work out, when you see like, wait, 4s, 7s, all that's going away. So 1/3 times 1, sure. But sometimes you don't see that. When you don't see that, you may have to write them out so that you see what's left, know what to put at the end. So again, if you understand the process, that's what allows shortcuts, right? Because you understand how I can take a shortcut here, a shortcut there. If you're just memorizing, then they look like a whole bunch of different kinds of problems. When reality is they're all the same, just some clean up much nicer. But yes, there are definitely some things you could do. And then again, I threw this number 6 one out here. On number 6, I said, I'll give you a hint on this, but this is an example where people get lost on a test. They get up here and they go, oh, okay, what is this? This is like a 4 times 5, and a 2 times 5, and a 3 times 5. What? And they're trying to play around with this and make it fit some strange sum when the reality was they never bothered to check, is it arithmetic or geometric? And I don't know if you know this, we'll talk about it again tomorrow, but geometric says there's a common ratio. And a common ratio, you remember geometrics, a really simple geometric might be something like that, right? And it's really easy to tell that 4 over 2 is 2, 8 over 4 is 2, right? 16 over 8 is 2. And if you have that common ratio, then it's geometric. Sometimes it's not so easy, but check it out. If it's geometric, 1/10 over 3/20 would equal 1/15 over 1/10. Let's see if that's true. What's 1/10 if you multiply it by the reciprocal of that? What do you get? 2/3? What's 1/15 if you multiply by the reciprocal of that? 2/3. This is not strange. This is just a geometric with a common ratio of 2/3. And what you would then do is go, oh, I have an infinite geometric. And then you'll dig out your formulas out of your long-term brain, which again, you might have forgotten this. But anybody remember the formula for an infinite geometric sum? Anybody for the star of the day? Nobody? Y'all remember T1 over 1 minus R? If it's infinite geometric and the ratio is a fraction. So you would learn tomorrow or the next day, you would take the first term and put it 1 over that ratio. And you would be done as soon as you simplify. I think it's 9/20 or something. But anyway, again, you will have to have this checklist in your brain. So if you're looking at this and going, well, oh my gosh, I forgot all this. It's okay, we'll go back over it like you haven't seen it. Except we're just going to go over it a little more quickly because I'm expecting some of this to fall in line and some of this to be stored in that long-term memory. If not, then you might have just a little bit more time spent on the weekends. All right, anybody see like number 7? This is another one that's kind of weird. I kind of snuck in there, but you would go down this checklist and you're like, wait a minute, this is really weird. It's not geometric, and maybe you check that over that, and that over that, and that over that, and that over that. You don't get a common ratio. It's not one of these weird ones, but look, 2 times 5, 3 times 5, 4 times 5, 5 times 6, 5 times 8. That's not fitting any pattern. Anybody remember this? We did one of these last year. Remember these?
Oh.
What do you see? Times a half, times a half, times a half, and then right here, times a half, times a half. What did I basically do here? I took 2 geometrics and I wove them together just to screw with you. And that's what you see sometimes in these. That'll be on your checklist. You know, you'll go down there. Is it arithmetic? No. Is it geometric? No. Is it one of these strange sums? No. Oh, wait a minute. Is it 2 geometrics woven together? Yes. And if you have this checklist, again, we've got 7 or 8 days to do this. If you have the checklist, you'll get there and you'll go, oh, sure enough. And then you'll just take first term of this one over its ratio, first term of this one over its ratio. And you'll add each of those. It'll add the infinite sums up, and then you'll add them up and get them. But I'm not going to do a lot of that tonight. I just threw a couple of these out there just to show you that they might look like they're a strange sum, but might not be. And that you, by the time you take this test, you'll have a list of about 6 options. Maybe not even that. Maybe we'll consolidate it a little bit. But you'll have to literally, some of them they'll be obvious what to do. When they're not obvious, you go down your checklist and you check. Because I will, you know me, I'm going to check what you know. And I'll put a couple out there that maybe seem like they're a strange sum, but they don't really fit it because you can never see that pattern. But then some will be back to obvious. Like, what do you do here? Difference of 4, difference of 4, difference of 4, difference of 4. Right? Lead terms, 2, 4, 6, 8, whatever. 1 on the top, sounds like a strange sum. So how would you set this one up? Out front, 1/4. Inside, and this is really important that you write these out. Check it out. A half minus a sixth. A fourth minus an eighth. Still nothing cancels. A sixth minus a tenth. Okay, something canceled. It's not back to back. What would the next term be? Not a 7th and an 11th. What would it be? Yeah, because 2, 4, 6. So the next one would be 1/8 minus 1/12. Okay, what happened right there? Back-to-back terms canceled. So without writing all these out, can you figure out what's going to be left over after you canceled everything? How many terms do you have in the front? A positive 1/2 and a positive 1/4. Okay, so what do you think you're going to have left at the end? 2 negatives, right? What are they going to be? Now, I know it's easy to look up here and go, well, the last term would be 120 minus 124. It's easy to see that the last term is going to be negative 1 over 24. What's the second to the last term going to be? 22, right? Not 23, because this pattern was what? 2, 4? Then this is going to be 24, 22. And that will save you the trouble of having to write all of these out and start canceling like crazy. You tracking with me? So if you see these patterns, now if it had been infinite, second you see 8 and 6 back to back, just go, everything else cancels, bring those down. And if you're looking at this right now and going, seriously? That common denominator? I totally hear you. I manipulate my problems so that they're not too bad. Sometimes I even let you use your calculator and say, hey, set these up, show all your work, but in the end you can use your calculator. I haven't decided on this test yet what I'm going to make you do. But sometimes I do let you use your calculator if you'll show me your work. But I won't let you use it without showing me work because your calculator literally does sigma notation. Your calculator can recognize patterns. You know, like I can hit my calculator and I can go 0.3333. If I 0.333333, if I put enough threes, it goes, oh, I know what he meant. He meant 1 3, or she, or whatever. Sometimes it can see those patterns. I could do 0.246, 246, 246, 246, and if I do it enough times, it goes, oh, I know what they meant. So at some point, you're going to have to show me the math, but sometimes I will let you use a calculator to clean that up. Okay, great. We have no time for this last one. I'm going to get you started on this last part, but I want you to see what you can do on it. We'll finish it up tomorrow. You've learned this before, and again, I wrote this up on a day I was going to be absent for people to learn it. But the key on this second part is this. What do you notice about this? What does the numerator look like? It looks like an arithmetic sequence where we're adding the same thing every time. What does the denominator look like?
Geometric.
Geometric. Now these have to be infinite. But if you see that, there's a trick to these. I'm going to take this, and I'm going to look down at the geometric part. And what is the common ratio there? What are you multiplying by every time? Looks like I'm multiplying by a 3, doesn't it? Now ignore the top. If I'm multiplying by a 3, here's the trick. I'm going to take that thing that I'm multiplying by, I'm going to flip it and negate it. So basically find like the negative reciprocal. And I'm going to take that number, and I'm going to multiply the original problem through by it. So it gives, like if it's 3, I make it a negative 1/3, negative 1/3, negative 1/3, negative 1/3, negative 1/3, negative 1/3, and I get a new function. Are you with me? Then I take these two and add them together. So I take the original problem, I multiply everything in it by a negative 1/3, negative 1/3. Now I slide them over so that they'll line up. Because when I multiply that by a negative 1/3, it has a new denominator. And I slide it over because I'm going to need to add it to this. Negative 1/3, negative 1/3, negative 1/3, forever. And then when I add everything up, look what happens. I get 1 minus a 1/3 s, 2/3 s, 4/3 and nothing, 4/3. And then here's the key. That and that, 3/9. That, 3/27. And guess what that creates? This part will always be an infinite geometric sequence. And what's my formula for calculating an infinite geometric sequence? First term on top, 1 minus the ratio. And the ratio is a positive what? You multiply the top by a 1 and the bottom by a 3. So a 1/3. So all I have to do at this point to take care of this is to find the sum of that. First term, 1 minus a 1/3. Add it to the 4/3. It's still there, right there. And then once you're done adding and simplifying all that junk, get s by itself by multiplying by 3/2. And that's the second kind. And again, the key to that is arithmetic on top, geometric on the bottom. Hey, do the best you can with it. We'll talk about it a little bit tomorrow before we get into arithmetics and geometrics. And 4 more days till a 9-day break. And maybe more, who knows? I'll find out in my second period meeting tomorrow.